Welcome to this lecture on understanding processors, where we treat the CPU as the computer's brain and walk through its core ideas. In this talk, we'll explore what a CPU actually does, how its architecture and data flow determine performance, and why cache, clocks, and evolving designs matter, so you can connect the hardware picture to the way software runs in practice. This slide zooms into the CPU package to show its main parts and how they coordinate. The control unit directs data flow, the ALU performs arithmetic and logic, registers hold immediate values, caches speed accesses, and internal buses move signals at nanosecond scale. The diagram highlights how these pieces interact tightly to turn instructions into precise, ordered operations. Here we follow the instruction cycle. Fetch the next instruction from memory into the instruction register, decode the opcode into control signals, and execute the operation in the ALU while updating registers. The flowchart emphasizes how each stagehands work to the next, and how correct sequencing and control signals translate binary code into real actions inside the processor. Clock speed sets the pace with a quartz oscillator generating ticks, but raw gigahertz isn't the whole story. Real throughput equals clock ticks times useful work per tick, so efficiency inside each cycle matters a lot. The graphics contrast high-throughput designs that do more useful work per tick with inefficient ones that waste cycles, reminding us to look past just headline clock numbers. Computation is built from tiny electronic switches up to complex functions. MOSFET transistors act as the fundamental on-off elements. Those transistors combine into universal logic gates like NAND, NOR, and NOT, and gates integrate into adders, decoders, and multiplexers to form the higher-level functional blocks that implement programmable behavior in hardware. Modern processors break complex instructions into smaller micro-ops and push them through a multi-stage pipeline shown here. Instruction queuing, operand fetch, ALU work and write-back proceed in overlapping clock cycles, so different micro-ops are handled in parallel. This pipelined approach boosts throughput but also requires careful coordination to avoid stalls and ensure correct results. To multiply performance, chips either add complete physical cores or use simultaneous multi-threading to keep units busy. Multiple cores provide true parallel hardware, while SMT interleaves instruction streams, so a core can do more work per clock. The slide shows how both strategies increase overall throughput, letting systems complete more tasks in the same amount of time. Caches hide the slow main RAM by keeping frequently used data close to the ALU. A tiny fastest L1 cache sits nearest the core. A larger L2 serves the core, and a shared L3 provides on-chip capacity for multiple cores. Predictive prefetching tries to fetch data early, and this layered hierarchy minimizes latency while balancing capacity and speed. The MOS 6502 case study shows the limits of purely data-driven analysis. Researchers produced large datasets and statistical patterns, but gained little functional insight until they applied domain models and hierarchical design thinking. Interpreting data requires architectural understanding, since domain models reveal how design decisions map to observed behavior and enable meaningful conclusions. This comparison contrasts a processor's fixed, fabricated logic with the brain's adaptive, plastic networks. Processors are precise, serial engines whose behavior is set at manufacture and can fail catastrophically if a transistor breaks, while brains route information in parallel, adapt connections over time, and can reroute functions around damage for graceful degradation. Looking forward, three trends stand out. 3D chip stacking increases on die bandwidth by stacking memory and logic vertically. Heterogeneous cores mix high-power and efficiency-focused units for better performance per watt, and post-von Neumann paradigms add accelerators and coprocessors, including AI and quantum elements, to explore new computing models beyond traditional CPUs. In closing, the processor remains the deterministic heartbeat of computing, translating stored instructions into precise action across layered abstractions. Appreciating cycles, cache behavior, microarchitecture, and limits helps developers write faster, smarter code by maximizing efficiency per clock, leveraging cache tricks, and respecting power, thermal, and bandwidth constraints for real-world performance gains.